Welcome 2100/1100. You both have the opportunity to do simple harmonic motion. So this video is for both classes. And first thing I want to say is, somewhat ironically, the procedure or obtaining the data is probably the most difficult part of this lab. Learning how to take good data rather than actually taking the data and analyzing it. Oh, okay, maybe analyzing may be a little bit challenging as well, but this particular lab deals with timing, and most of your error is going, if not all, is going to come from your ability to time accurately. So the author instructs you on somewhat of a systematic way on how to go about minimizing that error. So I want to draw your attention to procedure. Now it says, A, since the result of this experiment depend on your ability to measure the period accurately, it is worth spending a few minutes practicing timing and determining timing uncertainty. So the first part of this video is for practice. I'll have a mass on a spring oscillating up and down, and that's just for the sole purpose of you gaining practice on how to time these periods. And what you're supposed to do is, by the way, both classes have essentially identical procedures and analysis. There is one correction I want to make with 2100. I'll bring that up after I go into detail about this procedure on measuring. But other than that, they're identical. So what you want to do is time 2 periods, and then time 2 periods again, and then again and again. So the author says do this several times. Now, I'm not even going to pretend I know what several means. I pick 5. We'll do it 5 times, or I'll do it 5 times. Well, let's all do it 5 times. So we will measure 2 periods 5 times. And what we want to do then is determine the standard deviation of that data set. And don't worry, we don't have to go into that lengthy procedure for finding the standard deviation. We are given an approximation for the standard deviation, and that approximation is, well, we have these 5 measurements. What we do is we find the maximum time and the minimum time. We take the difference and we divide that by 4. And that is our standard deviation for the purposes of this lab anyway. By the way, so in the 2100 lab manual, it says take min or max minus min and divide it by 3. But in the 1100 lab manual, it says take the max minus min and divide by 4. So which one is right? What I went ahead and did, well, I was curious as to how they even came up with that approximation. I went online and found that indeed it's divided by 4. And then they also further explained logically how that approximation is even valid or reasonable or logical. Anyway, so if I was 2100, I would suggest just dividing by 4, not 3. So we're on the same page. Max minus min divided by 4. That is going to give us a standard deviation that we're going to use in this lab. And this isn't for our analysis. This standard deviation that we are determining is just to help us fine-tune our timing capabilities. So once we're done with that initial step, we're done with it. So we take, we measure 2 periods 5 different times, find the standard deviation. Now, if that standard deviation is above 0.2 seconds, we're instructed to go back and do it again, essentially practicing and figuring out the standard deviation a second time. And we want to get it down to below 0.1 second. And once we get it to 0.1 second, it's like we're good to go. Okay, we've gotten enough practice. We are confident that we could take accurate measurements, and then we proceed. By the way, 2100's lab manual says 0.15 0.5 second or less, but 1100 says 0.1 second or less. So which one do we do? Well, I'm just going with the 0.1 second, the one with better accuracy, right? But ultimately it's up to you and your instructors. But that is the only difference between the two classes. By the way, so somebody in my neighborhood just got a new dog and it's been barking nonstop. It just stopped about 20 minutes ago. So you might be hearing that in the course of this video. I can't do anything about that, so sorry. Anyway, let's see. That's what you'll see initially before we start collecting our real data, is that Bob oscillating up and down. And what I did was, or what I will do, is film this. It's going up and down, up and down. And I did a trial run. When I'm watching this, I count 2 periods, and this is how I do it as instructed in your lab manual. I start with -3. So when it's at its lowest position, that's -3, -2, -1, 0. I start the clock. Keep counting 1, 2, stop the clock. When it gets to 2, you stop the clock. So that is the time for 2 periods. I write that down, record it. Now this thing is still bobbing up and down, and I go ahead and do it again. -3, -2, -1, 0, 1, 2, and then write that down. It's still oscillating, so I do it yet a 3rd time. And before I was able to do it the 5th time, I ran out of oscillations. So I just rewound the video and continued to time and get my times for 2 periods another 2 times. And then I had my 5 measurements of time. I found the standard deviation, just found my max time, my min time, took the difference, divided it by 4. Oh, also, when I did, when I took the difference, it was only 0.03 seconds, and that's before dividing by 4. After I divide by 4, that's like 0.007 something, which is 13 times lower than my targeted 0.1 second. So hopefully this only just takes one trial, and you'll find that your timing capabilities are honed in. You have great reflexes, hand-eye coordination, and you don't have to do this several times. So the only issue you might have, well, the one I had, was actually I had to rewind the video several times because I'd be counting -3, -2, -1, 0, start the clock, 1, 2, and then forget to stop it at 2. Okay, let me start again, and then I messed up again doing some other thing. So that'll be your biggest challenge, is like remembering start at 0, stop at 2. But anyway, this may sound tedious, but we really want to learn how to time accurately to get good results, right? You don't want to go through this whole video and take data and then in your final analysis find that there's a large amount of error. What did I not analyze it right? Am I not doing the correct unit conversions, or using the wrong formula, or I mean, as a result of my timing? Let's just eliminate that right off the bat. Let's eliminate our error associated with timing. So one last thing. They want you to, when you start taking your data, record the number. Well, let me back up for a second. If we want to measure the period of something that's oscillating, we could for sure just measure one period. But since accuracy is totally dependent on reaction time, or I should say, because our reaction time could possibly lead to such a large amount of error, not only do we want to learn how to accurately time something, but we want to time several number of periods, right? And then with that final time, we just divide by the number of periods that we time to get the length of one period. And by doing so, we drastically decrease the error associated with that initial measurement. So they expect or would like you to have an error of no more than 1%. So to have an error of no more than 1%, they want you to measure a number of periods. This is for your real data. They want you to measure the number of a number of periods that take a certain amount of time. What time is that? That is at least 100 times the amount of your original uncertainty. So let's say your standard deviation was like 0.1. I mean, that's large from what I got when I did it, but let's just say it's 0.1. So if you multiply that by 100, that is what? Actually, I'm going to look at my notes and let me put you on pause and I will continue this thought. Hold on. Okay, sorry about that. So as I was saying, the author wants you to determine the periods that you measure with at least accuracy to within 1%. And to do that, you take your standard deviation, multiply it by 100. So if your standard deviation was 0.1 seconds, multiplying that by 100 would give you 10 seconds. So how many periods do you measure? It depends what mass we're considering here, because you'll find that each mass has a different period. Bottom line is you want to measure enough periods so that the duration of those periods that you choose to measure is at least 10 seconds in length. I put you on pause. I wanted to grab my standard deviation just to remind myself what it was. As I mentioned, well, it's 0.0075 for my first trial. So multiplying that by 100 gives me 0.75. So I would need to measure enough periods so that the total length in time would be at least 0.75, which is kind of ridiculous. I mean, that's just one period for the particular weight that I was using. I guess it doesn't matter if you're that accurate. I guess you could only measure one period if you wanted to, but I wouldn't do that. I would measure a handful. And hopefully that's your problem. Hey, you're so damn accurate that your biggest concern is just deciding how many periods you need to measure. As an example in the lab manual, it says like, let's see. If your uncertainty was 0.15 seconds and your period is 0.6 seconds, you would need at least 15 seconds total, which is 25 bounces. So you would need to measure 25 periods, whatever that time is, divided by 25, and there's the length of your period. But I really don't think, based on how I've determined my standard deviation, that you're going to run into that where your error is so large you're going to need this large number of bounces to time to get reasonable accuracy. But anyway, I know that traditionally when you're in the lab, this part is totally overlooked and a lot of students are confused by it. So I wanted to include it in this video. And again, I mean, it's ironic. I think that the largest part of this video for sure is going to be me talking about this timing uncertainty. But as I said, hey, it's worth investigating, and well, the author found it important to include it, and we are going to follow the lab manual, and we are going to get good results. So there you go. What I will do now is put you on pause and get a weight on that spring oscillating so you could determine what your accuracy is or what your standard deviation is. By the way, the author of the lab manual instructs us to find a weight that allows us like the easiest period to measure. And what I take by that is like the largest weight, because the amplitude is so large, and it's moving slower as it hits the amplitude before it starts to go back up, and so it doesn't. It's easier to start and stop the clock, but hey, why do the easiest one? Let's do the hardest one. I'm gonna do the smallest weight, where it's gonna be moving the quickest. I mean, after all, if we could get that down, then we'll for sure be like right on target with the others. And again, that's the one I personally use to find my standard deviation, so you shouldn't have any problems with that. I'll put you on pause and get your standard deviation. So I need 5 sets of times, and I want to start the clock at 0, stop it at 2. So this is what I would do: -3, -2, -1, 0, 1, 2. And that would give me my first time. So I'll let this run and let you do that. Let me put you on pause. I am going to give it another push. Hold on. In case you need more oscillations. All right, I think that's about enough. I'll put you on pause. Okay, welcome back. At this particular point, one of 3 things has happened. One is that you've taken your 5 different measurements of time and you have determined the standard deviation of that data set. If you haven't, put me on pause. Okay, you're back. And you found that it is 0.2 seconds or less. That means you're good to go. Your timing is good, and we're going to start the experiment now. The other situation is that that Bob didn't oscillate up and down enough times for you to take those 5 measurements. So what you need to do is rewind, watch it again, get the rest of your measurements. The third situation is that, yes, you indeed got your 5 measurements, you determined the standard deviation, but it was above 0.2 seconds. So in that case, you want to also rewind, go back, and do it all over again. See what your new standard deviation is. Remember, you should get it to below 0.1 second. Practice, practice, practice. Now, when you've done that, we are ready to get to the first part of the lab. And that is determine the period for small, medium, and large amplitudes. So what I'll do is I will set, I have 5 weights. I'm going to pick one of them and give it an amplitude of 1 centimeter. That will be our small. I will give it an amplitude of say 5 centimeters. That will be medium, and then give it an amplitude of 10 centimeters. That will be our large. So you want to determine the period for those 3 different scenarios. And what I will do is I will indicate somewhere in the background of this bob oscillating up and down the mass of the bob and its amplitude. I mean, you'll be able to see it anyway, right? I have a ruler behind the bob as it goes up and down, but I'll just throw the amplitude up there anyway. And by the way, this part of the lab doesn't call for you to know what the mass is, but if you know what the mass is, when we get to the second part of the lab, we won't have to redo this measurement. Like, we're knocking it out for both parts. It'll make sense to you when we get there. So let me choose a mass, get it in motion 3 different times, and you determine what that period is. So I'll put you on pause. Okay, so you just did the first part, determine the period for small, medium, and large amplitudes. We are now ready for part B. When you see these weights oscillating up and down, they'll be posted in the background. So your first run will say mass 1, the second one mass 2, so on and so forth. Part C is to simply get those masses and weigh them. So let's just go ahead and knock that out now. So here's the information that you're supposed to take in part C. Mass number 1 is 22.4 grams. Mass number 2 is 45.3 grams. Mass number 3, 96.6 grams. Number 4 is 129 grams. And number 5 is 172 grams. And by the way, you need the spring, the mass of the spring as well. That is 35.4 grams. So watch the next part of this video and you'll be able to do part B. And after that, we'll do the very last part that we need. Okay, I'll put you on pause. Okay, ladies and gentlemen, we are now at the end of the lab. We need only to do part D. So I'm assuming you've read what it is, you fully understand it, so this is self-explanatory. The author suspects that we could read this with an error of plus or minus 0.5 millimeters. Personally, I think we could do much better than that, but let's just assume that is indeed our error. Our initial spot of the bottom of this hanger is 7.55 centimeters, 7.55. So let's throw some weight on this hook and stretch it out approximately 10 centimeters. Okay, let me put you on pause. Okay, let me explain what I did. I simply placed 40.0 grams on this hanger and it reached a new equilibrium position. Now I know what the author meant by our accuracy is probably good to plus or minus 0.5 centimeters. This thing is moving around a bit. It's still oscillating, and I do not want to hang around here for another 10 minutes waiting for it to stop. So what we are going to do is take a measurement and call it a day. So that measurement is 16.62 centimeters. On your end, it might look a little different, but that's just because the camera angle. So 16.62. And that's a wrap. That's it, we're done. I get to go inside of a warm house and you get to do your analysis. Well, I'll probably go inside and do the analysis as well. I'm curious to see what kind of errors we got. But this is a fun lab, this particular one. I enjoyed it. And I'll see you next week.